Okay, good morning, good afternoon, everybody. I would like first to thank the organizers of this online workshop, and I hope we benefit out of it. So I will talk about the power inequality for the numerical radials. Everybody knows the power inequality, but today I will talk about a new progress, very new progress in this regard. When I sent Vahid the title of my talk, I was hesitant because the power inequality is well known, but at that time we had a submission about something new in the power inequality, and luckily we got it published just 2 days ago by linear algebra and its applications. So I will talk about this very new result on the power inequality. So the technical abstract is shown here. The idea is we want to discuss the power inequality, but for fractional powers, not for integer powers. The well-known power inequality, is this one. So I will use my pen to designate things. So this is the well-known power inequality. This is known when k is an integer value. If it's positive integer, this is the inequality. And we have the reverse inequality if k was negative. So this is well known. What we will be doing, I am going to present to you, is this version, which is a fractional version of the power inequality. The t values are between 0 and 1. So in this case, of course, we need to talk about well-defined powers, fractional powers like this. And this means we're talking about positive matrices, but in the case of positive matrices, these are trivial results. So basically we'll talk about accretive and accretive deceptive matrices. So the main result will be to prove this inequality for the values t between 0 and 1 when a is accretive deceptive. However, if t is accretive, our conjecture, this is still correct, but when a is accretive, we could not prove it for the whole range between 0 and 1. We just proved it for the t values between 0 and half. However, again, we believe that the inequality is still true when t is between 0 and 1. I'm not going through the definitions, and these are just standard notations. We just need the definition of the numerical radius. Everybody here knows it. And we just also need this identity. This will be crucial in our analysis. We relied completely on this identity to make our proofs. These are standard notations. Just to remind you, the matrix is called accretive if its real part is positive definite. Accretive deceptive if the real part and imaginary part are positive definite. If in case you see this notation, gamma n, we just mean the class of accretive matrices. Basically, our approach relied completely on the geometric meaning of accretive matrices. So the geometry will be very important. So that's why I'm just plotting this image to remind you of the meaning of accretive matrix. Basically, we have a sector, these arrays, and the numerical range lies within that sector. This is the meaning of accretive matrix. On the other hand, if the numerical range lies completely in the first quadrant within a sector, we call it accretive deceptive matrix. So this is an accretive deceptive matrix. This is an accretive matrix. I will go back to these graphs, these figures, when we start the proofs to understand the geometry and the formulas we have. So again, the basic power inequality is the one you have on the screen, that WAK is less than or equal to WKA when k is a positive integer. This inequality is known for so long. The reverse version when k is negative. So now if you're dealing with negative powers, you have the inequality reversed. and this is, to my knowledge, this was approved in 2010 by Choi and another colleague of Choi. I'm not sure if it existed before that, but this is the reference I know. So basically, the power inequality is known for integer powers, whether they are positive or negative. For the positive powers, we have it the normal way. The negative powers, it is reversed. Why is the power inequality important? The idea is that the power inequality resembles submultiplicativity. Just let's recall that the numerical radius is not submultiplicative. So in general, this inequality, unfortunately, we don't have the submultiplicative property of the numerical radius. Unlike the norm, the operator norm satisfies the submultiplicativity. And that's one reason dealing with norm, the operator norm, is much easier than dealing with the numerical radius. Not only that, not only the numerical radius is not submultiplicative, it is not submultiplicative even if you're dealing with the same matrix. So if you have WA cube and you split the A cube, you cannot distribute the numerical radius. We have counter examples for this. So the importance of the power inequality is kind of, it resembles submultiplicativity. So let me call this partial submultiplicativity. So WAK is less than or equal to this. So this is kind of a submultiplicativity behavior of the numerical radius. This is one reason the power inequality is really important. Now, our talk will be about discussing the power inequality. So we're looking at the relation between these two quantities, but if t is not necessarily an integer, if t is a fraction. So as a first step, we're looking at fractions between 0 and 1. Of course, now we start asking, what about fractions between -1 and 0? What about larger fractions? For example, what about 1.5 or 2.7? So fractions that are larger than 1. We will talk about these in what's coming. So to talk about WAT, we need this power to be well defined. So now we want just to remind the audience of the meaning of A to the T. When we talk about powers, fraction powers of matrices, usually we refer to two classes: positive matrices, and this is the trivial scenario. More generally, we talk about accretive matrices. Is it only these? No. Just to be precise, when we talk about A to the T, we can define these powers for any matrix whose spectrum avoids the negative axis. So if the spectrum of the matrix does not intersect the negative x-axis, we can talk about these powers without any problems. But again, usually accretive matrices are the easiest, at least, to deal with. Now, what is the definition of the fractional powers? This is the definition. I think most of us are familiar, at least, with the form. It is the Cauchy integral formula for matrices. Usually, we call this Dunford integral. Basically, what this says is we have a matrix, we have the spectrum of the matrix, but again, this spectrum avoids the negative x-axis. We take any curve that contains the spectrum. We call this gamma alpha here, and we do the complex integral. This is the definition of the fractional power of A. Now, this definition again works for any class of matrices whose spectrum does not intersect the negative x-axis. In this talk, we will focus on accretive matrices. However, dealing with complex integrals usually is not that easy. And sorry, the references don't show in my slides for a technical issue. We have another formula. We have another formula for the fractional power. And this one deals with real integrals. So we don't have any complex integrals anymore. And this, in many cases, makes this formula easier than the Dunford integral. So here T is between 0 and 1. We're dealing with fractional powers, and we're dealing with the principal branch of the root function. Now, as an application of this last identity, as an application of this identity, for example, we can prove that if A is accretive, then any fractional power of A is also accretive. Not only that, but there's another observation that we will need in our proofs. If A is accretive, we said the meaning of accretive is that we have a sector and the numerical range lies within the sector. This is A. Now, the good thing about A to the T, so for example, if you take A to the half, it's not only accretive, but then the sector shrinks by half. So if the sector angle was 60 degrees for A to the half will be in the sector of angle 30. This is very nice. So if A, let's call it, if A was in S alpha, A to the T will be in S T alpha. This property will be really important in our proof. We have very basic lemmas. The first lemma is really simple, and we know it. If A is positive and you have a power outside the norm, we can take it inside the norm, provided that T is positive. The second lemma is what I just said. If you have an accretive matrix and you take a fractional power, it will be accretive, not only accretive, but you will shrink the sector, the original sector. If the angle of the original sector was alpha, you multiply this alpha by T to get the new sector. And another very important inequality is this inequality about accretive matrices. So we can play with the fractional powers, TT, on the left and right. So if you have the real part of the fractional power of A, that would be bigger than, but you take the fractional power outside. Why is this property important? At least one reason that justifies the significance of this inequality is that if A is accretive, this can be considered as another proof that A to the T is also accretive, because real T is bigger than a positive matrix. So this is an important property for many reasons, and we will see the significance of this property in the proof. Now, the first observation and the first motivation behind this work is basically the original power inequality. So as we said before, the original power inequality was WAK is this than or equal to WA, but the K outside. Then we asked, what about if K was a fraction, and we will need A to the fraction power to be defined. So we're dealing with accretive matrices, and with just by using this power inequality, we can prove this fractional version. So basically, we can prove that if A is accretive, if you take this fractional form, this is 1 over a positive integer only. So this is not for any fraction. This is for 1 over 1, or 1 over 2, 1 over 3. So this reverses the original power inequality. So this fractional version tells us if you have a fractional power, you can take it out, but with bigger than or equal. And the proof is very simple. This is the proof. This is the proof. How do we prove it? We just write A as A to the 1 over K to the K. And we apply the original power inequality because K is integer. It's less than or equal to this. And now if you compare this with this, you take the power 1 over K, and this is the proof of this simple inequality. Again, this was our first motivation. And starting with this, we started asking, okay, this is correct for these fractional powers, 1 over K. What if we replace the 1 over K by any fraction between 0 and 1? Can we have the same inequality? Our conjecture says yes. So we believe that this inequality is correct. So if you have a fractional power inside the W, you can take it out, but with bigger than or equal. We did some simulations on Mathematica, and all computations support this conjecture. All computations support this conjecture. Now, did we prove it? And so in our recently published work, did we prove it? No. So what did we prove? Let's see. So again, we conjecture this for accretive matrices. The first observation is if we're dealing with positive matrices, this is a trivial inequality. This is just an equality if A was positive. So there is nothing to talk about positive matrices. Now, what we proved is if the matrix is not accretive, deceptive, then we have the inequality correct. So if the matrix was accretive, deceptive, and T is between 0 and 1, we can prove the inequality, and we will show the proof. We will show you the proof. But before we go further, also, we can prove that if T is between -1 and 0. So basically, if T is between -1 and 1, we have this inequality. For all fractions between -1 and 1, we have this inequality. So in this case, we know everything about the positive integers. We know everything about the negative integers in terms of the power inequality, I mean. And now, if A is accretive deceptive, we know everything between -1 and 1. Now, again, this does not resolve our conjecture, because our conjecture is that this is correct without the word deceptive. Our conjecture is this. If A is accretive, then the inequality is correct. But we could not prove it completely. We will see how to prove it. So as a corollary, we will prove that if A is accretive, then the conjecture is correct, but when T is between 0 and half. And again, we can just prove it between between -half and half. But we will mention the case between 0 and half because the other case is very similar. So this gives like half solution for the conjecture. Now I want to prove, so for the proofs, I'm going to present all the proofs. The proofs, by the way, are very simple. They rely completely on the geometry of accretive matrices, our understanding of this geometry. I will prove the accretive deceptive case in the end. So I'm leaving the proof of this result to the end. But I like to go through some corollaries that follow. For example, this one. So now the question is, how to obtain the accretive version from the accretive deceptive version. So this is what I want to show you in the beginning. So we want to prove that WAT is bigger than or equal to WAT when T is between 0 and half. And again, A is accretive. When A is accretive. This is what we want to prove. So the idea is this. I will make some figures to explain these assumptions. So we have an accretive matrix. This is good. Now we go back to one of the properties. So if A is accretive, that means the numerical range lies in the right half plane. But when you say accretive, it could be above or below, like this, the x-axis. And we have some sector like this. Now the idea is, if A is accretive, we just mentioned this property about A to a fractional power. This shrinks the sector that contains the original matrix. Now, because the maximum value for the angle is pi over 2, when we take half, that shrinks it to pi over 4. So basically, if A is accretive, when we take the power half, the numerical range will belong to a sector of angle pi over 4 necessarily, regardless of the original one, because the original matrix lies in the right half plane. So the angle maximum can be pi over 2. If we multiply it with half, that gives pi over 4. So now I have the fractional power A to the half lies within an angle of pi over 4 above and below the x-axis. So if we draw this pi over 4 and this pi over 4, my numerical range will be between them, something like this, let's say. Then I can multiply this a to the half. So this is the numerical range of a to the half. I can multiply the numerical range of a to the half by e to the I pi over 4. What does that do? That rotates the numerical range counterclockwise by an angle of pi over 4. So basically what you get, you will have something in the first quadrant. So instead of having it in the first and second quadrant, then because of this rotation, you will have it in the first quadrant, and that means your new matrix becomes accretive deceptive. So now the point is we converted somehow. We started with an accretive matrix, but by taking the power half, then multiplying with e to the I pi over 4, we are having an accretive deceptive matrix. Why do we want an accretive deceptive matrix? Because the conjecture is solved for accretive deceptive matrices. So now I'm going to apply this theorem. This is the main theorem, basically. I want to apply it, but we will apply it not on the matrix A. We will apply it on the accretive deceptive matrix, which is e to the I pi over 4 times a to the half. This one. So let's see. Again, t is between 0 and half, and that means I can write the t as r over 2, r between 0 and 1. Let's proceed. So what is w a to the t? Because t is r over 2, I can write it this way. Then because w is a norm, I can insert this number because this is a complex number of modulus 1. So I can do it. Then this a to the half has power r, and this has power r. So I can write them all with the power r. So these are basic properties. And by the way, when we deal with matrices, we need to be very careful how to deal with these powers. And using our geometric approach, we prove this. So if we have time, I can show you the proof of this, how to move from this line to this line using our understanding of the geometry. So now we have this power r here, and r is between 0 and 1. But at this stage, if you look at this matrix, this is accretive deceptive. Remember, this is accretive deceptive. And the conjecture is solved for accretive deceptive matrices. What do we mean by this solved for accretive deceptive matrices? We mean if you have a fractional power inside, you can take it outside with bigger than or equal. And again, because w is a norm, you can cancel e to the I pi over 4, and you're reaching a to the half. But remember from the beginning, we proved from the original power inequality that if you have a to the half, that's bigger than or equal, and you can take the half out. So you're having r over 2, and over 2 is exactly t. And this is the proof. This is the proof when the matrix A is accretive and t is between, unfortunately, we could not prove it, unfortunately. We could not prove it for t between 0 and 1, although we believe it's correct. But this is the proof if t is between 0 and half. It's a very simple proof relying on the main result. As I mentioned earlier, okay, this is what happens if t is between 0 and 1. And just to make this point clear, this is correct. This is correct, even if we're talking about negative powers. So between negative half and half, we proved this in the same paper, but this is the proof for positive values. Now, what about values that are bigger than 1? So the power inequality is this. This is like our difference. And the k is integer. The k is a positive integer. Now the question is, what if these are powers that are not integer but larger than 1? For example, what about WA to the power 2.5 or 3.7? Can we still have this power goes out with this inequality with the same order? The answer is yes. The answer is yes, but we have some conditions. Again, because you're talking about fractional powers, that means we're talking about accretive matrices. So we have another consequence of these results. If we have an accretive matrix, and this is honestly, this is not a nice condition. This is not a nice condition. I believe we can get rid of this condition, but we have it here because this is how we need it in our proof. The way we proved it, we need this condition. But again, it's not a nice condition at all. So if a to a certain power is accretive, for example, if a to the 10 is accretive, or a to the 11 is accretive, or a to any power is accretive, then the power inequality will be correct for any value between 2 and k. And the m is not necessarily an integer. This is the significance of this result. So for example, if a to the 10, let's say k was 10, so if a to the 10 was accretive, what we're saying is that this inequality is correct for all values between 2 and 10. Integers, fractions, irrational, this will be correct. This is a nice consequence, but at an extra cost. We have the condition a to the k is accretive. This is one thing. The second thing, we're seeing this number 2. We're seeing this number 2 because this is related to our proof for accretive matrices and the value half. So the 2 and the half, these are the reciprocals of each other. Again, we have these conditions because we proved it this way, but maybe if we come up with a new proof that does not depend on the same methodology, we can get rid of these conditions. So again, this is an extension of the power inequality to any power larger than 2, but an extra cost that a to the k has to be accretive. Now I'm going to start the proof of the main result, which is about accretive deceptive matrices. And nicely, the proof relies as a first step on a very simple observation like this. All the proof, the first step to the whole conjecture and the proof was done geometrically. So after we understood the geometry of these things, we translated it into algebraic proof. So the idea is this: imagine you have any matrix, not necessarily accretive or whatever, and you're dealing, I'm looking at the numerical radius. The numerical radius basically measures the farthest distance between the origin and the numerical range. So in this figure, this line, this blue line, the length of this blue line segment will be the numerical radius. Now, at this point exactly on the boundary here, because this is a point in the numerical range, so it will be something like this. There will be a unit vector x node, so that ax node with x node inner product gives me this point. And in that case, the absolute value of this inner product will be equal to the numerical radius. Now, as a complex number, this is r e to the I theta for some r some theta. R is the absolute value. And if we denote theta by this gamma, if the argument of this complex number was gamma, then WA is going to be exactly this. Basically, what is this? Basically, this is, we just make this rotation. So if you imagine you rotate the numerical range by the angle, this is gamma, this here is the angle gamma. So if you rotate it back, so you multiply with e to the minus pi gamma, this will be on the real axis. This will be exactly the numerical radius. Basically, this is the result, and this is the proof. I believe this proof is, we did not see it. We did not see it written anywhere, but I believe people working with the numerical radius know this proof. And it's not a new proof, but we could not find it written in any reference. So if we go quickly over this proof, so if WA was this absolute value, and gamma was the principal argument of this complex number. Then this inner product is R. This represents R in the complex plane times e to the I gamma. And this because we had this exactly equal to the numerical radius. So we have this identity. Now, the real part is Hermitian. We know that. So W of the real part of any matrix is always less than or equal to W of the same matrix. So now if we go to this line, the operator norm of the real part is Hermitian, so the norm and the numerical radius are equal, but the numerical radius of the real part is less than or equal to the numerical radius without the real part. So we remove the real part, and because the numerical radius is a norm, we can remove this to get this. So basically this line tells us that this quantity is less than or equal to the numerical radius. Remember what we want to prove. What we want to prove is that this norm is equal exactly to the numerical radius. So we will prove this in two steps. In the first step, we prove that the norm is less than or equal to the numerical radius. In the second step, we want to prove the other way. So how do we prove the other way? Let's go. So the norm is equal again because this is Hermitian is equal to the numerical radius. Now the numerical radius is basically, this is the definition. It is the supremum over unit vectors, and this is the matrix we are interested in, inner product X. And for sure, because we're taking the supremum over all unit vectors, and X node is a unit vector from the beginning, this is bigger than or equal to this because we picked one vector out of these unit vectors. And at this point, we just take e to the minus I gamma out, and we replace AX node. Remember AX node, X node. We wrote it as the absolute value times e to the I gamma, and this absolute value is exactly WA. So in this step, we replaced AX node, X node by e to the I gamma times WA. These are cancelled, and we are left with the real part of WA, which is just WA. So this proves that the norm is bigger than or equal to WA, and here we proved that the norm is less than or equal to WA, and this proves again, let's forget the proof. Let's forget the proof and focus on the result, that if you have the numerical range and you have this value here, you take this angle gamma, you rotate this back by negative gamma to get the numerical radius. This was crucial in our proof. Now, why is it crucial? And I think now it's the time to tell you why we could prove it for active deceptive matrices, but we could not prove it for active matrices. What is the reason for that? So now, based on this understanding, I have, if you have an active deceptive matrix, the numerical range lies in the first quadrant. So if you take this numerical radius, this is the angle gamma, then for sure gamma will be between 0 and pi over 2. This is a very important observation, that gamma will be between 0 and pi over 2. So when you rotate this back, when you multiply it with e to the minus I gamma, again, the red disk or ellipse or whatever, it lies in the first quadrant. If you rotate it by this value, it will be either, it depends on gamma, but it will be for sure either in the first quadrant or in the second quadrant, or maybe in both of them like this. So this is what we get after rotation. But in all cases, when you make this rotation, this is the point, this is the key point. In all cases, when you multiply e to the minus I gamma with A, if you start with an accretive deceptive matrix, the result will be accretive. This is the main observation. What do you mean by the main observation? Let's do this for accretive matrices. Imagine instead of having an accretive deceptive matrix, imagine you have an accretive matrix like this. So in this case, you're looking at the numerical radius, right? You're looking at the numerical radius. The numerical radius is roughly, this is it. We take up to here, like W. So this is gamma. This is gamma. Now, if you rotate this back, if you multiply it by e to the minus I gamma, we don't have any guarantee that the new numerical range lies in the right half plane. Depending on gamma, this numerical range can go back to the third quadrant. And in this case, this rotation is not accurate. This was our problem in the proof, and that's why we could not prove the result for accretive matrices, but we could for accretive deceptive matrices. We needed a lemma to make our proof. This lemma is really nice, and again, it resembles our understanding of the geometry of accretive deceptive matrices. So it's like complex numbers. If you have like a complex number like this. So what is the result? The result says if you have an accretive deceptive matrix, and this is the Cartesian decomposition. So E is the real part, F is the imaginary part. Sorry, H is the real part, K is the imaginary part. Then we have this formula for A inverse. So A inverse will be E, this is E, plus IF, this is F. Now, what is the observation here? The observation here is, if you start with an accretive deceptive matrix, when you take the inverse is not accretive deceptive. It will be accretive, but it will not be deceptive because the imaginary part will not be positive. So taking the inverse of accretive deceptive matrices does not necessarily give an accretive deceptive matrix. So this lemma was really crucial because we need it in our proofs. We needed to prove that if A is accretive deceptive, then any fractional power is accretive deceptive. So again, we need this result that if you start with an accretive deceptive matrix, does it mean that taking fractional powers is accretive deceptive? Yes, we will prove it now. Remember, this result is well known. Everybody knows it, but for accretive matrices. So we know that if A is accretive, fractional powers are accretive matrices. But now the new result is if A is accretive deceptive, then the fractional power is accretive deceptive. Now to prove this, we used the integral representation of A to the T. I'm not going through this proof, and by the way, there is a typo. There is a typo somewhere here. We should have an S, but that's okay. I want to go to the proof of the main result about accretive deceptive matrices. These are technical lemmas. So I like to show you the case of accretive deceptive matrices in the remaining time. So the main result of this work is if A is accretive deceptive, we have this conjecture, and T is between 0 and 1. Again, we can make little changes to the proof to make it also work for -1, 0, but we state it here for 0 and 1. So let's start with an accretive matrix. We're taking this X node as before. So this is where the numerical radius is attained. And we are rotating this by e to the minus I gamma. The result will be accretive deceptive. So the real part of e to the minus I gamma A will be positive for sure. So e to the minus I gamma will be accretive. This will be very important to use the properties. So now what is the point? The point is, remember we proved just minutes ago this inequality without the T, this identity without the T. So if you forget the T, we just did this. Now just take the power T for both sides. We're dealing with positive integers. Then, because this is accretive, again, it's all about the geometry. Because this is accretive, the real part is positive. But if you have a positive power for the norm, you can take it inside. So this is T here. Then, because this is accretive again, we have another inequality that if you take this power on the real part, you can insert it. You can insert it with less than or equal. It is one of, I think people who work on in accretive matrices know this inequality. We mentioned it in the introduction. Then we can distribute this power. So we can write this as e to the power t and a to the power t. We mentioned this property before also. And now this is less than or equal to the supremum. This is just an exponential. So basically this is less than or equal to the supremum over these values. And this supremum is exactly the numerical radius of a to the t using the theta identity. So this gives the proof. This gives the proof that WT A is less than or equal to WAT when A is accretive deceptive. And as I mentioned, the fact that it is accretive deceptive was extremely important to make this accretive. And to guarantee that this is accretive, we need the original matrix to be accretive deceptive. So this is the proof of the main result. I think, I would like to thank you for listening. I think I presented the main stuff I want to present. And now if you have questions.